So today we're going to look at Exam 4, Chapter 6 and 7, review. And we'll work from the review document. I've got the key up here on the board. And you'll notice in bright space, if you go back and look at the available documents, I've updated the review documents to reflect removal of some problems that weren't appropriate for these two chapters. I don't know how they got in there, but in fact, I do know how they got in there by accident, but I had kept them in previous semesters and used them as bonuses, but I got thinking about it, and this particular topic is better addressed in the next chapter, chapter 9. And even as bonus, it would be a distraction. So those, and you'll see them on the board here. This first one is marked out because it's subject that we haven't covered yet. So that being said, let's get going with some selected items, and I have had time to highlight them. So whenever you see this yellow in this document and in the posted document, bright space, same way. So let's see. Just for our viewing audience, I'll keep track of the ones that we're working on here. Which of the following statements is not true of balancing chemical equations? So that means we've got to go and look at each one of them. Subscripts in the reactants must be conserved in the products. Nope, sorry. You take care of the subscripts when you write the compounds correctly. And after that, they are wholly untouchable. Subscripts do not change during the balancing process. B, how did that get in there? That one should have been moved down to E. Okay, so I've got a problem to correct. Oh, got another visitor here. All right. So let's move on. Coefficients are used to balance the atoms on both sides.
Yes.
Yep, coefficients, yep, that's true. Phases are often shown for each compound, but are not critical to balancing an equation. That's also true. And the law of conservation of matter must be followed. Yep. And the way you know that that's happening in a chemical equation is you have the same number of atoms of each element on either side of the equation after it's balanced. That means that mass has been conserved in the process. So the only one that's wrong is A. This one, the law of conservation of matter.
Well, my E, it says all of the above statements A through D are true.
Oh, I've got an older version then.
Yeah, yours is B up there.
So yours has been corrected.
Yeah.
Okay.
Well, I mean, my answer is still A, but E says all of the above statements are true, A through D. On mine.
Okay. Oh.
Yes, sir.
Oh, okay. The key then may have some discrepancies. We better watch out for that, because the key was developed on an earlier version, and when I corrected and updated the unkeyed version, I didn't translate that into the keyed version. So we'll keep a close eye and let me know if, I'll tell you what, as we go, I'm going to mark to check those items as we go. Just don't let me get away with anything.
I mean, I had A as my answer too, and I seen E, and I was like, it's wrong too. Yes, these are all the above statements A through D are true.
Yeah. Oh, okay. That's another item that needs to be corrected. Yeah, I get your point.
So that one's got two answers.
Yeah, you're right. Okay, how about 3? When the following equation is balanced using the smallest possible integers, what's the number in front of the substance in bold type? So we would do PCl 5 plus water will yield H3PO4. Oops. I'm running out of room here. Let's move it down some. Leave a little space in here for coefficients. Okay, so if we use our budget method, we have a polyatomic here, but this polyatomic is not present on both sides. So we have to account for each element separately: phosphorus, chlorine, hydrogen, and oxygen. So on this side, we have 1 phosphorus, 5 chlorines, 2 hydrogens, and 1 oxygen. And on this side, we have 1 phosphorus, 1 chlorine, hydrogens, 4 hydrogens, right? 1 there and 3 there, and 4 oxygens. Okay, so for the time being, we can leave the phosphorus alone. Chlorines, let's see, we don't have any standalone elements to preserve for the end. So we could just go right down the line and say, all right, well, let's do chlorine. So we would need a 5 over here, right? That would give us 5 chlorines. It'll also change the hydrogens. So 5 plus 3 is 8 hydrogens. Okay. Now, if we want to make 8 hydrogens here, we need 4. So that's 8 hydrogens and 4 oxygens. And as luck would have it, we're balanced. And we can see that we're balanced from the budget itself. So the coefficient for HCl should be 5. D on my key. On yours too. Okay. All right, let's see. We can see everything on 4, so we'll go ahead with that one. All the following are clues that a chemical reaction is taking place, except
Reactive is smaller.
yeah, a solid forms, that's a key. Bubbles form, color change occurs. Now, a color change is a clue, but it's not definitive, because you can get color changes with just physical changes, not chemical. But it's still considered a clue. And in combination with other clues, you can deduce that a chemical reaction has occurred. A flame occurs, that's definitely a chemical reaction. Well, I can think of possibilities, but I'm not going to bore you with those details right now. So yeah, a reactant is smaller. It's usually difficult to tell that a reactant has decreased in amount. I suppose it's possible, but this is the best answer, B. All right, 4. Let's see, who's next? 5. I better scroll this one. And there's 6. We'll get 5 and 6 together. Okay. When the following equation is balanced using the smallest possible integers, what's the number in front of the substance in bold type? Okay. All right, we do have elements in this one to hold out. Fe3O4. Al2O3 plus Fe. Okay, so aluminum and let's see, iron, this Fe. Okay, this is what you'll notice is if we take this as -2 and that's -8, that iron cannot have a whole number charge. So it's not something I'm going to hold you to, but just an indicator that this could be a compound with an odd charge, but it's probably a combination of two forms of iron. One of the irons is +2 and the other iron is +3, and they can be combined in such a way as to give you the fractional, like 3 divided into 8. It's not going to be a whole number. But for our purposes, we don't need to know that. This, in fact, is probably, what is that reaction? Thermite. This is a thermite reaction. If you've ever seen a video of thermite reaction, it is extremely violent. The railroads use it to weld their rails together because during the reaction, it produces iron. And that is a perfect weld between the two rails with a lot of heat. Okay, so let's balance this. We could probably do this without the budget, but I should probably stick to it. Aluminum, iron, oxygen. So we have 1 iron, 1 aluminum, 3 irons, and 4 oxygens. We have 2 aluminums, 1 iron, and 3 oxygens. Okay. I wonder if this is going to, this might be a place where we can use that cross multiply trick. So wherever you find an odd even comparison, these are both odd, so I wouldn't bother with those. Plus, we want to hold these elements out till the end. So I look at the oxygens. There's a 3, there's a 4. What if we put a 4 here and a 3 there? That will make 9 irons, 12 oxygens. And this will make 8 aluminum and 12 oxygens. Okay. Now we can go for the aluminums and irons on the opposite sides. So we need, what, 9 irons over here? And we need 8 aluminums over here. Okay? That's one of those cases where you kind of have to step back and say, all right, I know this thing is going to give me trouble because of this 4-3 comparison. Not always the case, but in this case, it worked out. If you try doing just in order, you'll probably get there eventually. But this is a quicker route to use that cross multiply trick. There's another one further down the line. I forgot this one was there actually. Actually, the trick of the trick is to figure out which ones to cross multiply. All right, number 6. Which of the following statements about chemical reactions is false? In balancing a chemical equation, all subscripts must, wait a minute, we've done this before. Okay, we've done one like this before. This is a similar statement to before, and it's false. So if we don't have any other squirrely ones down here, like all the above, 2 of the above, we can stop here. Which of the following is false? That is false. So we don't actually have to look at the rest of them. We know they're true. And we can save a few minutes. All right, how about 7? Balance the following equation. What's the number in front of the underlying substance? Okay, C2H6, C2H6, which is ethane. I'm going to leave out the phases. They're all gases. and that'll save me a little bit of room. CO2 plus water. That's the case with any combustion of an organic compound like this. When you burn this, you always get CO2 and water. Okay, so let's set up our budget. Carbon, hydrogen, oxygen. 2 carbons, 6 hydrogens, 2 oxygens. 1 carbon, hydrogen, 2 hydrogens, and 3 oxygens. I think that's right. That's it. 2, 8, 9, 10. So just 10. Okay, this is 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, we're good. All right. The temptation here, since you see an odd and even, is to use the cross multiply. But notice that this one is a standalone element. Cross multiply only works when those elements, odd and even elements, are in compounds. If they're standalone, then you're going to save that to last anyway. So we don't want to use the cross multiply. What we want to do is go ahead and see how much we can do holding this one out. So if we go to carbon, we can get 2 carbons out of that. We can get 4, 5 oxygens. And then we can get hydrogens. If we put a 3 here, that gives us 6 hydrogens. And balance the 6. That also gives us 3 plus 4 is 7 oxygens. Okay, so now the trick is fractional coefficient. We need 7 oxygens on this side, and they only occur in that element. So if we do 7 halves, that will give us 7 oxygens. But we need to reduce this to the nearest whole number. So we need to multiply the whole thing through by 2 to get rid of that fraction. Right, so that gives us 2 here, 7 there, 4 here, and 6 there. So the coefficient in front of oxygen is 7. Okay? That was our fractional coefficient trick. And just so you know, any of the hydrocarbons, they're in a series. These organic compounds where you have a carbon and hydrogen, you're going to have so many carbons, and then each of the hydrogens are going to be 2n plus 2. Any of that series, except for methane, CH4, all of them, you'll have to use that fractional trick. So if you see, say, octane, like that, burn, you will definitely have to use the fraction trick. All right. I think I've got one in here, another one like that. Okay, we can see this one. When the following equation is balanced, what is the number in front of the underlying substance? So, yeah, it's starting to get a little weak on you. Try this one. And still push the button. Here we go. All right. So we're starting off with aluminum oxide and sulfuric acid. Is that? Yeah, it's aqueous. It's a solid acid. And we get aluminum sulfate. And water. Okay, now let's see. Sulfur occurs in this compound, and that compound, and that's a polyatomic ion that does not change. on both sides. So we can use it as a balancing group. So what we've got is aluminum, oxygen alone, not counting these oxygens. We got hydrogen and we got sulfate. Okay. So we've got to be aware that these oxygens are confined to that group and these oxygens are separate. So we've got 2 aluminums here, got 3 oxygens there, 2 hydrogens, and 1 sulfate. And on this side, we have 2 aluminums, 1 oxygen, because we're not counting that oxygen, and 2 hydrogens, and 3 sulfates. Okay, so where do we start? Well, aluminums are good. These oxygens, we could start there. But I have a sneaking suspicion we need to go with the sulfates first. No, we need to go with the okay. I put a 0 there. Put a 0 there. Okay. Let's try it just in order. So if we put a 3 here, that gives us 3 oxygens. It also changes to 6 hydrogens. Okay. Now, if we do hydrogens, we want 6 hydrogens over here, right? So that gives us 6 hydrogens and 3 sulfates. And we're done. Okay, so to answer the question, the coefficient in front of water is 3. I almost made it more difficult than it was. And 11. Let's see, we're going to balance this one. And what's the coefficient in front of the hydrogens? All right, 11. Newcomers. What's that one? SN. 10, right. Stannum. And we're going to react it with sodium hydroxide. Good old lye. Grandma's lye. Only we're not going to make soap with this one. And then we get this compound. SiO2 plus H2. This is sodium stannate. That's a polyatomic ion. But we don't have any polyatomics that don't change across the arrow, so we have to take them all separately. 10, sodium, oxygen, and hydrogen. We've got 1 tin, 1 sodium, 1 oxygen, 1 hydrogen. We've got 1 tin, 2 sodiums, 2 oxygens, and 1 hydrogen. Oops. 2 hydrogens. There we go. Okay, let's see. I'm going to hold this one out. Right now, it's not a problem, but it could be. Sodiums. What if we go with sodium? We're going to hold hydrogen also. If we do sodium 2 here, that changes oxygens to 2, hydrogens to 2, and we're done. That was too easy. So the answer is A. Right, remember, just because we don't write it doesn't mean it's not there, right? There's a 1 here, and there's a 1 there, and there's a 1 there. All righty then. Let's see. There's another one that got crossed out. This is going to be covered in chapter 9. So I crossed that one out. Let's see, 24. Balance this one. What's the number in front of the underline? Okay, so we start off with lead. We'll leave out the phases. Silver nitrate in solution yields lead 2 nitrate. Has to have a 2+ charge to balance these 2 minuses, plus silver. Solid. Okay. See, is that showing? So we need to find the coefficient for that one. Let's see, we've got nitrates here on both sides. That's good. You know what? We can balance this one without a budget. See how many nitrates are over here? 2 nitrates, 2 nitrates, 2 silvers, 2 silvers, 1 lead. We're done. In the beginning, you probably want to budget everything. But at some point, you'll start seeing trends, patterns. And you can look at an equation and say, wait a minute, I don't need a budget. Just a couple of numbers and we're done. So coefficient is 2 in front of this one. There's another one. 26 is crossed out. Let's see. Get down to another yellow one. Here we go. All right. Write a balanced equation showing the reaction between iron 3 oxide and carbon monoxide to form iron metal and carbon dioxide. So this is a word problem. And we've already got the answer there. So pay no attention to that man behind the curtain. We're going to work from the word problem. And first we have to build our compounds. We're going to react iron 3 oxide. Iron 3 oxide. Oops. Like that. So in order to make that balance, we need a 2 here and a 3 there. Okay. And after that, we don't need the charges. We're going to react that with carbon monoxide. Carbon monoxide. And it's going to give us iron metal and carbon dioxide. Carbon dioxide. There we go. Now we just need to balance it. All right. Let's see. We're going to hold this one out. Let's do a budget for this one. Oxygen, carbon, iron, oxygen, carbon. So we got 2 irons here, 1 iron there, 4 oxygens here, and 2 oxygens there. In carbon, we got 1 carbon here and 1 carbon there. So we need to focus on oxygens. Yeah, oxygens. So if we do a 2 over here, what does that do? Got 2 carbons and 4 oxygens. Okay. Uh-oh. Okay, we're going to go around the barn. So our oxygens are good. Carbons are not. If we do carbon here, could we have started someplace else? No, we couldn't have. Okay, so let's slog through it. if we're going to make 2 carbons here, then that gives us 2 here, that gives us 5 oxygens. So what we need is 1 more oxygen on that side. So can we get 1 more? We've got 4 now. We need 5. So what if we change this to, no, if we do that, we've changed the carbons. Okay. What if we go up to, just, let's bump this up 1. Let's go up 3. That'll make 6 oxygens and 3 carbons. Oops. 3 carbons, 6 oxygens. Then, if we come over here and do 3 carbons, that gives us 3 oxygens and 6 oxygens. Okay. Oh, and then we need to fix the iron. There we go. All right. That was kind of that's like chasing cat around the barn. You never know if you're going to catch them until you do. I don't have any special tricks for this one. We just had to slog through it and try different things. And as luck would have it, this attempt here, where I changed from 2 to 3, I needed to get, since this was odd on this side, I needed to even things out. So instead of going from anything times 2 is even, and 4 wasn't working. So the only possibility I had was to go up to 3 and make 6. And as luck would have it, that worked out. Because you've got a 3 here, and if you have a 3 here, then now you've got an even number of oxygens. That was, actually, that's the focus here, the trick. You got an even number of oxygens on that side, you need even on this side. So even on this side means you need 3 there. So that would have been a better logic to go here first.
So I think that's what you did on the key.
Is that what I did on the key? Okay.
Yeah, because it's got a 1 in front of the carbon.
Okay, so the key is a better teacher than I am right now.
Well, I mean, you did.
Yeah, eventually, if you write your compounds correctly, eventually you'll get there. It just, some ways are quicker than others. Let me see, those are too easy. Let's go, how about this one? Balance this equation. Silver nitrate in solution, calcium chloride in solution, silver chloride solid, and calcium nitrate. There we go. Okay. So we do have a polyatomic here. What type of reaction is this? It's a precipitation. The double replacement with a precipitation. Right? We just swapped silver with calcium. Now we got calcium nitrate and silver chloride. And the driving force behind this one is the formation of the solid. Okay. Let's see, is there any more to that? No, okay. All right. So do we need to do a budget on this one? Most of the time, these double replacement reactions are really easy. They balance beautifully. So if we did 2 here for the nitrates, that means 2 silvers here and two chlorides, one calcium. We're done. I think I need another marker. Starting to whip out on me. Let's see. I got this one. Oh, yeah. All right, that was 39. 40. This one might take some doing. So we're going to balance this equation. Magnesium, that's not doing too good either. Magnesium nitride. In this one, nitrogen is a -3 charge, magnesium is +2. Metal, non-metal. Then we have water and ammonia and magnesium hydroxide. There. Okay, so let's see. We don't have any, we have polyatomics, but they're not the same on both sides. So we're going to have to do a budget for this one. Magnesium, nitrogen, hydrogen, and oxygen. 3 magnesiums, 2 nitrogens, 2 oxygens, 2 hydrogens, and 1 oxygen. So let's see, that's 3, 4, 5, 6, 7, 8. 3, 5, 6, 7, 8. That's good. Magnesium here is 1. Nitrogen is 1. Hydrogen is 2. And oxygen is 2. Okay. Magnesium first. Did I write that right? You are exactly right. That would eventually dawn on me when it doesn't balance. So let's see. 1, 3, 4, 5, 6, 7, 8, 9. 5, 6, 7, 8, 9. Okay, we're good. Count for everybody. So, we got hydrogens in 2 different places here. What if we start with nitrogen? That would give us even number of hydrogens, right? 6, 7, 8. Correct? Okay. Now, how about magnesiums? If we do 3 magnesium, that will give us 3 oxygens. Okay. And no, 6 oxygens, excuse me. 2 times 3. And 2 times 3 is 6. And 6 is 12 hydrogens. We good so far? Now notice the ratio between hydrogen and oxygen here is 2 to 1. 2 to 1, 2 to 1. So really all we need is 6. That gives us 12 hydrogens and 6 oxygens. That was a little trickier. Okay. Oh, does it agree with the? Yeah. Okay, that was 40. How about, oh, I scroll that one. Go down here, okay. I suspect this one's going to be pretty easy too. Hydrochloric acid. I just can't get a good marker today. Hydrochloric acid. And calcium hydroxide. So what kind of reaction is this? Acid, base. So in an acid-base reaction, we should get a salt, calcium chloride, plus water. Okay. So we got hydroxide is broken up in the process. So we're going to have to budget this one. Hydrogens, chlorine, calcium, and oxygen. So we have 3 hydrogens here, 1 chlorine, 1 calcium, 2 oxygens. On this side, we have 2 hydrogens, 2 chlorines, 1 calcium, and 1 oxygen. Let's see, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. 4, 5, 6, 7. Okay. Let's see, we've got even odds here. Hydrogens in 2 different places here. What if we start with chlorines and put a 2 here? That also changes the chlorine, the hydrogens, to 2 plus 2 is 4. That changes our odd even to even. That's good. And then on this side, hydrogens, like a 2 here. That gives us 4 hydrogens and 2 oxygens. And we're done. All right. Okay. Oh, okay. This is the one I was expecting. This is the one with a cross multiply. This also has a cross multiply. So sodium. Tell you what. What I get from buying cheap markers. Sodium borohydride and boron trifluoride. Sodium. It's got to have a name. Sodium. Boron trifluoride. This would be boron tetrafluoride. Sodium boron tetrafluoride. That doesn't sound right. Oh, I ran out of space. Try it again. Come over here. Borohydride. That's what it is. Borofluoride. EF3 yields sodium borofluoride plus, that's called diborane. Okay. So let's do our budget first. Sodium, boron, hydrogen, and fluorine. We got 1 sodium, 2 borons, 4 hydrogens, and 3 fluorines. 7, 8, 9, 10. 3, 4, 8, 9, 10. 1 sodium, 3 borons, hydrogens, 6, and fluorines, 4. Okay. We've got borons in 2 different places here. And they're odds and evens. We've also got odd even for fluorine. But fluorine only occurs in one place on this side and one place on that side. So that's the key. If you try to use a cross multiply, be sure that you don't have it in 2 different places. But since we've only got fluorine in one place here and one place here, if we take that 4 here, four there and 3 here, then we get 12 fluorines, 12 fluorines. And then this is going to give us 5 borons. Right? This is going to give us 3, 4, 5 borons. And 3 more sodiums, right? Let me do a recount. 1, 5, 4 hydrogens, yep. 12 fluorines, okay, we're good there. 3 sodiums, borons, 3, 5, that's good. Hydrogens, 6 hydrogens, and fluorines are 12, okay. So we're good up to this point. Now, we're good here and here. Hydrogens and sodiums are off. So what if we say, let's focus on sodium. What if we say 3 sodiums? That gives us 3 borons plus 4 borons is 7 borons. And 12 hydrogens. Right? And then on this side, hydrogens, 12 hydrogens. We need 2 here. That'll give us 12 hydrogens, and 4 plus 3 is 7 borons. There we go. That did it. That was a little trickier. That's probably why most textbooks say balance by inspection. Because they don't want to spend 40 pages showing you all these tricks. Book print is expensive. And that gives the instructor something to do also. Let's see. Are we still in chapter 6? Yeah, we're still in chapter 6. Okay, we're good. 61. Balance this equation. C3H7OH. C3H7OH. So that's propanol. We can't tell what kind of propanol because there's several different versions. But you're all familiar with isopropanol, like rubbing alcohol. So if this is isopropanol, then you know what it smells like. But we're going to burn it anyway. Combustion reaction. What other type of reaction is a combustion reaction? Oxidation reduction. Automatically. If you see a combustion reaction, it is oxidation reduction. Okay, so let's see, we better do a budget. Carbon, hydrogen, oxygen. So we got 3 carbons here, hydrogens, 8, and oxygens, 1 there, 2 there, 3. We're gonna hold this guy out to the end too. Carbon on this side is 1, hydrogens, 2, and oxygens, 3. Okay, so where do we start? Well, I don't see any tricks that pop out right now, so I'd start with carbon. So if we say 3 carbons, that gives us 6, 7 oxygens. Okay. Hydrogens, we need 8 hydrogens. So if we do 4, that gives us 8 hydrogens. It also changes the oxygens to, let's see, 4 plus, is that right? 4 plus 6 is 10. Okay. All right, so we need 10 oxygens on this side, but the oxygen's in 2 different places. So we've already got 1 here, we just need 9 more, right? We need 9 more oxygens if we leave that one alone. Right? 9 halves oxygens will give us 9 plus 1 is 10. And then we have to get rid of the fraction. Right, so now we're going to have 2 here. We're going to have a 9 there. We're going to have 6 here. And we're going to have an 8 there. So 8, 6, 9, 2. There it is. The mistake that's often made is we need 10 oxygens. So we go over here and say, oh, I need a 5 in front of that. If you forget to look at that oxygen right there, then it'll sink your ship. The reason I know that is because I've done it before. Okay, how about this one? All right, so we're working from a word problem. Iron 3 oxide and carbon monoxide. 62. Iron 3 oxide. So that's 3 plus, 2 minus, means we need a 2 here and a 3 there. Plus carbon monoxide equals iron 2 oxide. 2 plus, 2 minus, we're good there. And carbon dioxide. Okay. So what type of reaction is this? Oxidation reduction. Here's the clue. Iron is 3 plus on this side, 2 plus on that side. Electrons must have been transferred. Okay, let's see if we can balance this. I bet we can do this one without a budget. If we need 2 irons, okay, 2 irons is good. Now we have 2, 4 oxygens, 3, 4 oxygens, 1 carbon. We're done. 1 number is all it took. And we're balanced. I guess the trick to this problem is writing the compounds correctly. There's always a motivation to each problem that an instructor puts on face. We don't just randomly slap them up there. There's a purpose. Okay. 68. Aha, okay. Here's your octane. Okay, octane, same stuff that you burn in your gas tank. Oxygen. And we're going to get carbon dioxide and water. So let's do a budget with this one. Carbon, hydrogen, oxygen. 8 carbons, 18 hydrogens, 2 oxygens. 1 carbon, 2 hydrogens, 3 oxygens. All right, do the carbons. 8. So that makes 16, 17 oxygens. Okay. Hydrogens. We need 18 hydrogens. 9. So that's 18 hydrogens. Now we have 9 plus 16 is 25. Okay. That's the only thing we have left is the oxygens. So if we put a 25 halves here, we're good. Get rid of the fraction. Now we have 2 there. We have 25 there, 16 there, and 18 there. Okay. These guys, those hydrocarbons are like that every time. The only one that doesn't do that is methane, which is AKA natural gas. All righty. Oh, we're getting into chapter 7 now. Let's see, let's scroll up. Okay, 73. An aqueous solution of ammonium carbonate is allowed to react with aqueous. Yeah. Aqueous solution of nickel 2 chloride. Identify the solid. So we have an aqueous solution of ammonium carbonate. Ammonium carbonate. Right? That's a 1 plus. This is a 2 minus. So we need 2 of those. We react it with aqueous solution of nickel 2 chloride. Nickel 2 chloride. So we need 2 of those. Okay, what's the solid? This is a double replacement reaction. Maybe we get a solid, maybe we don't. But what would you do? Well, you would swap this cation with that cation. So nickel carbonate, nickel 2 carbonate, just like that, right? 2 plus 2 minus. And then the other one is ammonium chloride, like that. Now, to answer the question, we don't have to balance it. We just have to identify what is the solid that's produced. We're told that these are already in solution. These guys right here, they're aqueous. So if you don't remember the rules, go to your chart and follow nickel across the top and go down to carbonate and say, is it grayed out? Did you find it? It's grayed out, isn't it? There's your solid. And we know that ammonium and chloride compounds are both soluble. Well, most chlorides are soluble, and all ammoniums are soluble. So there's your answer. NiCO3 right here. Is your solid. Most carbonates are insoluble. Except for sodium carbonate. That's one where we have conflict of 2 rules. And the sodium, the alkali metal, is above the carbonate rule, so it takes precedence. Sodium carbonate is soluble, but that's not part of our problem. All right, 75, let me scroll it and see if I can get 76 in there too. Yeah, 77 also. We'll do like that. There we go. 75. A substance that when dissolved in water produces a solution that conducts electric current very efficiently is called what? Yep. In the first case, it's an electrolyte. That's given. But if it is efficiently conducting electricity, it's a strong electrolyte. And in chemical terms, a strong electrolyte doesn't matter what the concentration is. What it matters is how well does it dissociate? How many ions per molecule does it produce? And a strong electrolyte will virtually completely disintegrate. Sodium, like sodium chloride in water. Sodium ions, chloride ions, it completely dissolves. Makes lots of ions to transfer the charge. So that's why it's a strong electrolyte. How about this one? 76. The equation silver oxide yields silver plus oxygen is what type of reaction? Okay, let's look at that. This is balanced for us already. This is a solid, and it produces silver solid plus oxygen gas. Okay. What type of reaction is that? Well, in the first place, it's going from complex to simple. It's a decomposition. Now, just because I name these here doesn't mean you're going to find them in the answer. Right? So you have to also look at the fact that these elements were at one time part of that compound. That means it's oxidation reduction. Okay, so what are our choices? Decomposition, oxidation reduction. Yeah, two of these. Okay, it's not a combustion because oxygen's not on the reactant side. And it's not a synthesis because that's opposite of decomposition. It can't be both. All righty then. What type of reaction is water always a product? Let's see what our choices are. Precipitation? Nah, you don't have to have water for that one. Synthesis? Could be, but it's not always. Oxidation? Could be, but not always. Decomposition? Not likely. There it is, acid base. Acid base always produces water as a product. In fact, that's the net ionic equation for an acid-base reaction. Protons from the acid, hydroxyls from the base, give water. Okay, let's see, what do we have? 80. Heard a ding-a-ling. No new names. The factors that most commonly cause chemical reactions to occur, all the following except. Okay, that most commonly cause chemical reactions to occur. A decrease in temperature. You have to read into this question, most commonly caused. There are rare occasions when a decrease in temperature will promote a reaction. But most commonly, an increase in temperature promotes a reaction. So A would be false, and we could technically stop there. Transfer of electrons, they can cause reactions. Formation of water, acid base, they cause reaction. Formation of gas, cause a reaction. Formation of solid cause a reaction. Why? Think about it. Why does the formation of a gas or the formation of a solid promote a reaction? If you've got aqueous solutions on this side, two aqueous solutions, and it produces a solid, what does that effectively do? It removes that compound from the reaction or makes it less available. It just drops out of solution. Okay? So when it does that, now it can't go in reverse, which reactions will do. It's removed from the reverse reaction, so it tends to continue to drive that way. As long as you've got enough reactant to make solid, it'll keep going that way. Similarly for gases, and it doesn't have to be aqueous, but if it produces gas, the bubbles take a product and remove it from the reaction environment. And it also tends to drive the reaction because now it can't go in reverse. That's why solids and gases promote reaction. Because if you form any of them, they are effectively removed from the reaction environment. And that goes by the name, it's called Le Chatelier's principle. We haven't covered that yet. No, okay. Maybe we will, maybe we won't. My mind's kind of dim on that right now. How about this one? An aqueous solution of ammonium sulfide is allowed to react with an aqueous solution of barium chloride. What's the coefficient of the solid in the balanced equation? Okay, for this one, we've got to go the whole 9 yards. 84. We got to take the word problem, ammonium sulfide, that's 2 minus 1 plus. So that means this has to be 2. Is allowed to react with the aqueous solution of barium chloride. That one's aqueous and barium chloride. Barium is an alkaline earth. Okay. So it's 2 plus charge, chlorine's a minus 1 charge. We need 2 of those. And that yields what? Well, it doesn't tell you. Barium sulfide is a possibility, right? Double replacement reaction. And then ammonium chloride. Well, we know ammonium chloride is going to be soluble. So if I had to guess, I'd say barium sulfate was the solid. And if you look in your chart, you probably will find a grayed out square. There's your solid. But the question is, what's the coefficient for the solid? All right, so that means we have to balance the equation. These are really easy to balance. We need 2 chlorides and 2 ammoniums. That takes to this one, that one, 1 sulfide, 1 barium. We're good. So the coefficient is 1. All right, 85, just barely chopped off. Here we go. So for this equation, which we balanced earlier, it says it's an oxidation reduction reaction. Is that true? Yeah, it's a combustion. It has to be. But the question is not, is it an oxidation reduction reaction? Why is it an oxidation reduction reaction? Yes, it is an oxidation reduction reaction, true. So it's either A, B, C, or E. So, this one might be kind of difficult. All right, let me put this one up on the board. See if I can help you make sense of it. And then plus 6 water. Okay. And we didn't cover, I don't think we covered I mentioned oxidation states but we didn't actually cover how to determine oxidation states. All right. So if this shows up on an exam, it better be a bonus. It better not be required because we didn't cover that material. I don't think we did. Did we? No, we didn't. Okay. So one of the rules is free elements like this have an oxidation state of 0, which is analogous to no charge. And since these are all type 3 compounds, non-metal, you really can't assign a charge to any of them. Hydrogen typically is +1. That makes 6 pluses, 6 minuses to balance it, makes this 3 plus. This one, oxygens are taken as -2, -4, +4. So the carbon goes from +3 to +4. So it is true, it's an oxidation reduction. We got that from our rule of thumb and the fact that it's a combustion reaction. Carbon is reduced. We didn't. Did we do the oil rig? Yeah, we did. Oil rig. Oxidation is reduction. Oxidation is loss. Reduction is gain. So this carbon has to lose an electron to go from 3 pluses to 4 pluses. So carbon is oxidized, not reduced. Carbon is oxidized here. Okay, that's fine. Carbon is oxidized there. What about the hydrogens? Or is it oxygen? Oxygen changed from 0 to -2, so it's reduced. So we get reduction here, and we get oxidation there. We should have done that. That's a shortcoming on my part. If we didn't do oxidation states, we should have done that in this chapter. I probably didn't include it because it wasn't in the textbook. Okay, so the answer is carbon is oxidized, oxygen is reduced. At least I don't think we did. We take a quick gander. No, we didn't. We did not cover oxidation states. You know what? I bet. Yes. We get it in chapter 18. Okay. So this is kind of premonition of chapter 18. Because chapter 18, we actually do get into redox reactions in earnest. And we learn how to determine oxidation states. Okay, that one's not a fair question for this one. So, if that question shows up and it's not a bonus, then call me on it. Because you should not be expected to do that right now. Okay? And if I accidentally put it in required section, then you'll get credit for it anyway, no matter what your answer. Right? It shouldn't be required. Bonus, maybe, yeah, okay, we could go bonus. How about this? How many electrons are transferred in the following oxidation reduction reaction? You know, we didn't cover that either, did we? No, I don't think so. Because you have to do oxidation states to do that. Okay, something's stinks in Denmark. The only way we could possibly do this one, simply because we have available to us charges. Right? So let me show you how this one works. You don't even have to know oxidation states to do this one. Now for the nonmetals, nothing but nonmetals, yeah, you do need to do that. But for the metals, you can do this one. It's a zero charge. Right? You know that elements don't have a charge. And then for this compound, this is -1, you know, from your polyatomics. That one has to be a +1. And this one, zinc nitrate, since this is -1, that's -2 total. This has to be a +2. And then silver is a 0. Okay, so we can tell, since we have metals in here, and the nitrate didn't change at all. So if we say zinc goes from that to that, it had to lose 2 electrons per zinc. And this one went from a +1 to a 0. So it had to gain 1 electron per silver. Okay? But we know that we have to have the same number of electrons go in the oxidation as the reduction step. If they don't, then you're creating electrons or you're destroying electrons. So in order to make them balance, we need 2 here, 2 there. Okay. So that should balance the equation. And to answer the question, it's 2 electrons are transferred for that one. Did I lose anybody? As long as you've got metal-non-metal interactions, you can usually do this based on charge alone. And we know what charges are because, well, we learned what the fixed charges were, right? For the alkaline metals, 1, alkaline earths is 2, aluminum group is 3, +3. Halogens are -1. Chalcogens are -2, pnictogens are -3. That's so that we can write the compounds. We need to know those values. Okay? Okay. How are we doing? I got 40 minutes. Let me see how much more we need to do. 89. You might be able to make it. An aqueous solution of sodium carbonate is allowed to react with an aqueous solution of magnesium chloride. The complete ionic equation contains which of the following? Okay, we need to do this one. An aqueous solution of sodium carbonate. Sodium carbonate, okay, aqueous solution, is combined with magnesium chloride. Right? Alkaline earth, 2+ charge, halogen -1 charge, we need 2 of them. And what does that produce? Well, it's a double replacement reaction. Magnesium carbonate, 2- 2+, that's good. And sodium chloride. Aqueous solution, we know. That's probably a solid. So look it up. Magnesium and carbonate, they form the grayed out box, I think. Correct? Okay, so that's a solid. Okay, now we need to balance the equation to give you the complete molecular equation. 1 sodium, we're good there. 1 carbonate, we're good there. 1 magnesium, 2 chlorines. Oops, I wrote this one wrong. That's a 2 minus charge, that's a plus 2 charge. There. So we need a 2 here. Now it's balanced. So the complete ionic equation would be taken from this one. In aqueous solution, you've got 2 sodiums, ions, and 1 carbonate in solution. You've got 1 magnesium in solution. And you've got 2 chlorides in solution. Now on this side, you got that solid, you can't break it apart. And then you have 2 sodiums and 2 chlorines, or 2 chlorides. There you go. Okay, that's the complete ionic equation. So which of these does it contain? 1 sodium? No, it's 2 sodiums. So that's not right. 2 carbonates? Nope, only 1 carbonate. 2 magnesium pluses? Nope, just 1. 1 chloride? Nope, it's got 2 chlorides. There you go, E, 2 chlorides. Actually on both sides. So our spectator chloride, 2 of them, is the answer. Now, the reason we know that that D is wrong and A is wrong is because the rest of them have coefficients, right? So we're taking coefficients into account. If we didn't have coefficients in there at all, then we'd have to get rid of one of these in order to find the right answer. But in the balanced equation, and that's another key, the complete ionic equation has to be balanced. While we're here, what's the net ionic equation? We'll get rid of the spectators. Then we have 1 carbonate, 1 magnesium, and some magnesium carbonate solid. That's your net ionic equation. Go into my bag again. Yeah, maybe it'll work, maybe it won't. You shake it down a little bit. Yeah, we can see that one. An aqueous solution of ammonium sulfate is allowed to react with an aqueous solution of barium nitrate. What's the solid? All right, we've got ammonium sulfate, ammonium sulfate. So we got 2 of these because that's a 2 minus, that's a 1 plus. 2 of those. That's aqueous solution. We're going to react it with what? Barium nitrate. Remember, all nitrates are soluble. Barium is a 2 plus charge, nitrate is a 1 minus. So we need 2 of those. Now, in solution, we've got free-floating ammonium ions, sulfate ions, barium 2 plus ions, and nitrate ions. So they get a chance to mix. So the cations and the anions are free to associate however they want. Well, this association is soluble. That one's soluble. So you're going to take this barium and swap it with that ammonium. Barium sulfate, 2 plus, 2 minus. And ammonium nitrate. That's soluble. Both for the nitrate and the ammonium makes it soluble. But barium sulfate, we look at that one and see. I'll be willing to bet it's solid. solid. Okay, so there's your solid right there. And anybody who's ever had a colon X-ray has been intimately associated with barium sulfate. I call it a barium enema. So you have to drink that fluid, clean yourself out the night before, and then you go into the doctor's office and the radiologist will fill up your colon with barium sulfate, and then they'll start taking x-rays. Why is barium sulfate a good choice? First of all, barium is a huge atom. It sucks up x-rays like nobody's business. So it gives you good contrast. But the other reason is barium sulfate is insoluble. So you don't get barium or sulfate flooding your system. It's not soluble, so it can't cross the boundary between your colon and your bloodstream. So barium is a good choice. Barium sulfate is a good choice. Or in medical terms, they call that a contrast agent. Okay. Oh, we need to look at this one. So this one's a diagram. And you know what? I'm going to have to shrink that down. Can I get away with this one? Which drawing best represents the mixing of aqueous calcium chloride? Let me get that up here first. 97. Aqueous calcium chloride and aqueous potassium sulfate. Okay, so what is that going to produce? Well, it's going to produce calcium sulfate. Let's see, that's correct. That's correct now. Calcium sulfate, 2 + 2 - that's correct. And potassium chloride is aqueous. Okay, we can balance this one real quick. 2 potassium, 2 chlorides, 1 calcium, 1 sulfate. This is a solid. You look at it. Calcium sulfate is the precipitate. Okay, now we're looking at a representation, a drawing that represents what happens here. So when this reaction is complete, what do you have left? Well, you have consumed your calcium and your sulfate to make that solid. So the calcium and sulfate ions are no longer in solution. Potassium ions and chloride ions are still in solution, plus you have a solid in them. Okay, so what we're looking for is a diagram that shows us before and after that is characteristic of that reaction. Let me shrink it just a little bit more. Maybe I can get it all on the screen. About 125. Yeah. Okay. Now we can see everything together. Except it's going to be kind of small for our viewing audience. All right. So let's process of elimination. I would start with the precipitate. Right? So there's a solid. It's got to be this one. Notice the A refers to this one and the B refers to that one. It's an artifact of Microsoft Word. So they're aligned at the bottom. So E is this one, D is that one, and so forth. There's your solid, there's your solid, there's your solid. So it has to be B, C, or D. Can't be any others. All right, we have to count for the solid first. Okay, how about what's left over? Potassium ions and chloride ions. Which one of these solids has that? There's potassium and chloride. There's potassium chloride, but there's only 1 in 1 of them. Right? Here you got 2 and 2. Right? That gives you a clue. Now let's check. B works for this and that. How about beginning? Calcium chloride. 1 calcium and 2 chlorides for B. 1 calcium, 2 chlorides, and 2 potassiums and 1 sulfate. There's your clincher. That makes B the answer. All right, now let's blow it back up so we won't have to swim. Oh, here, I'll just scroll. Let's see, how much time we got? I'll tell you what, let's come back to these. I got a whole bunch of these identify chemical reactions. I want to skip these and come back to them. 103. As a reminder, come back to 103. Well, let's go. There are a whole bunch of them there. Let's look at these guys down here. Oops, there we go. Complete ionic equation for barium hydroxide and hydrochloric acid. 136. Complete ionic equation for barium hydroxide and hydrochloric acid. So what we get is barium swapping with hydrogen to make barium chloride and water. So is barium chloride a solid? Or is it soluble? Soluble, okay. That's important. Now let's see if it's balanced first. 1 barium, 1 chloride, 2 hydrogens, 1 oxygen. It's already balanced. So if we do the complete ionic equation, this is a barium, wait a minute, that's not right. This is a 2 plus and that's a 1 minus. 2. Let's see, 2 chlorides. So that's 2, 4. There we go. Now it's balanced. Okay. Now we can write the complete ionic equation. 2 plus and 2 hydroxyls plus 2 hydrogen ions plus 2 chloride ions. And then we've got, still have barium in solution. And we have 2 chlorides in solution. And we have 2 waters. Pure liquid. There we go. Now the net ionic equation, right, would be 2 hydroxyls, 2 hydrogens, makes 2 waters. Simplified, 1 hydroxyl, 1 hydrogen ion makes 1 water for all acid-base reactions. But that's not the question here. We just wanted to complete ionic equation. And the driver for this reaction is the formation of water. Let's see, we're going to do acids and bases. Yeah, when we get to acids and bases, I'll introduce a topic that explains why that's the driver. Because when you get hydrogen ions and hydroxyl ions in the same vicinity, they really want to be together. And there's a mathematical expression for that. It's called the equilibrium expression. Okay. Oops. All right, that was 136. 138. Okay, 138 requires that you go all the way through molecular, complete ionic, and net ionic equation. So let's do that. 138. Molecular equation for copper 2 nitrate. Copper 2 nitrate minus 1 plus 2 is combined with sodium hydroxide, aqueous, and it makes, in fact, it tells you, solid copper 2 hydroxide. Plus sodium nitrate in aqueous solution. Okay, so let's balance it. These double replacements are very simple to balance. We need 2 hydroxyls. Now we need 2 sodiums, 2 nitrates, 1 copper, 2 hydroxyls. We're done. Just a 2 in front of that one, 2 in front of that one. Okay, now the complete ionic equation. We got a copper 2, oops, 2 in the wrong place, is aqueous. We have 2 nitrates. We have 2 sodiums. And we have 2 hydroxyls. Yields a solid and 2 sodiums plus 2 nitrates. There we go. So that should be the complete ionic equation. There's our copper, 2 nitrates, 2 sodiums, 2 hydroxyls, makes 2 sodiums, 2 nitrates, and there's our solid. Now the net ionic equation, you just look from the spectators. We've got 2 nitrates on both sides. We've got 2 sodiums on both sides. So copper 2 plus and 2 hydroxyls makes copper 2 hydroxide solid. That's your net ionic equation. Okay, now we go back to 103. Here we go. So we can do, in the remaining time, we can identify reactions. Now, you'll notice about this one, based upon the answer, there may be more than one answer. Okay? So don't be afraid to put, for these, don't be afraid to put more than one from the selection here in the answer box. Okay? Sometimes there's only one. In fact, there's one of them down here. I think there are 3 of them. We'll get to it. Okay, 103. Our reaction is 2 cesium solid plus fluorine gas yields 2 cesium fluoride solid. Okay, what are our choices? Well, we've got simple, simple, making complex. Okay. That's a synthesis. We've got element, compound. That's redox. Okay. We don't have any oxygen, so it can't be combustion. Decomposition is the opposite of synthesis, can't be that one. So it's got to be oxidation reduction and synthesis, A and C. How about 104? I'm going to have to scroll that one a little bit. Let's go down and scroll 105 also. Okay, in the interest of time, I'm not going to write the equation up here. Sodium sulfate and lead 2 nitrate forms lead 2 sulfate solid and sodium nitrate still in solution. So what do we have here? Well, it's a double replacement. There's also precipitation. What else? Well, sometimes it helps to look at the selections. What do you have? Is it an oxidation reduction? Sodium is still 1+ on both sides. Lead is still 2+ on both sides. And the polyatomics are fixed charge. So that's not a redox. And these double replacement reactions are rarely redox. There are some exceptions, but most of the time, if you got a double replacement precipitation, you don't have a redox. And it's not acid-base, right? There's no water over here. So precipitation is the only possibility. How about 105? Let's see. Oops. Yeah, I gotta scroll some more. There we go. So we've got ammonia gas and oxygen forms nitrogen monoxide and water. Yes, combustion, definitely. Oxidation reduction, you've got an element here, it's in a compound over there, plus it's a combustion, so it has to be redox. How about the others? It's not a synthesis because these are no more complex than those. It's not a decomposition. Right? So it has to be one of these two, oxidation reduction and combustion. The only ones that fit. And I'm going to have to scroll that one again. Chopping off our equation. There we go. We'll get those two. 106. How about this following one? You've got an element, and an element makes a compound. So that's definitely a synthesis. But that's not one of your choices. But you have an element in a compound, so that's oxidation reduction. It's not a precipitation because there's nothing in solution here. So this is the only one that works, oxidation reduction. So that's A. About 107. That's the same one as, yeah, it's the same answer as 106. Yeah. You're forming a compound from elements, which makes it oxidation reduction. Yep. That was also A. 108. Let's see, we have gallium nitride, forms gallium and nitrogen gas. We're going from a compound to elements. That's definitely a decomposition. Right, so D is an answer. We're also going from a compound to elements, which rule of thumb says should be redox also. So A and D are good choices. Not a combustion. Can't be a synthesis because it's already a decomposition. So A and D is the only possibility for 108. How about 109? Let's see, here we have HC2H3O2, that's acetic acid, vinegar, and cesium hydroxide, that reading correctly? Yep. And it forms water and a salt of that cation and that anion. It's definitely acid base. But the acid base reactions, I can't think of a single example which would be a redox also. And they're never in quotes. They're never redox. And there's no precipitate here. So it has to be acid base and that's it. The only choice. Let's scroll 110. So 110. See, carbon and oxygen makes CO2. That's combustion. Yep, there you go. It's also oxidation reduction. Yep. Right. Element to compound synthesis. There you go. A, B, and C. About 111. Let's see. We've got nitric acid, sodium hydroxide makes water, and sodium nitrate. That's definitely acid base. There's no precipitation. There's no oxidation reduction. So this one is B. Let's see. Make room for another. 112. Let's see. Potassium bromide, silver nitrate. Looks like we've got a double replacement making a precipitate. So it's a precipitation reaction, not acid base, no oxidation reduction. Potassium's the same on both sides. Silver's the same charge on both sides. Bromine's the same charge on both sides. And nitrate's a fixed charge. So it's not oxidation reduction. It has to be only precipitation. How about this one? Calcium plus hydrogen makes calcium hydride. Well, it's definitely a synthesis, but that's not a choice. We're going from element to compound. It has to be oxidation reduction. There's no acid base. There's no precipitation. Yeah, so that has to be A. Oops, I scroll this one. 114. Let's see. Oxidation reduction again. Synthesis is not a choice. Combustion is not a choice. So oxidation reduction is the only one that fits. How about this one? Zinc hydrochloric acid makes hydrogen gas and zinc chloride. Let's see. Oxidation reduction. Oh, yeah. Zinc is an element here and a compound there. Acid base, no. Precipitation, nope. This is also known as a single replacement, where you take that zinc and kick that hydrogen out. Just a single replacement. That's not a choice, though. Oxidation reduction is the only one that works for this one. For the ones that are, the answers that are given. How about this one? Sulfuric acid, barium hydroxide makes water and barium sulfate. That's definitely acid base. And yes, an acid base that makes a precipitate. Sure enough, acid base precipitation is correct. It's not oxidation reduction. We've had no change in, no movement of electrons in this case. So that one's B and C. 117. Zinc bromide in solution, silver nitrate in solution makes zinc nitrate, silver bromide. We're making a precipitate out of these two solutions. So that's definitely one. No acid base, no oxidation reduction for a double replacement reaction. So this one is only C. One 18. C3H8, which is propane. Right? Same stuff you burn in your grill, or if you have a tank outside and all your utilities are gas driven. This is the gas they use. This is the combustion. Right? So it's definitely that one. It's also oxidation reduction. Combustions and oxidation reduction are well, combustion is a special case of redox. It's not a synthesis, not a decomposition. So it has to be AB. 119. We've got phosphorus. Oxygen makes phosphorus decoxide. No, tetraphosphorus decoxide. All right, this is a synthesis, definitely. It's a combustion with oxygen, and which makes it automatically oxidation reduction. So this one's A, B, and C. Now 120. Synthesis, combustion, and redox. Synthesis, combustion, redox. That was also A, B, C. $121, need to scroll. Okay. Decomposition. Got mercury 2 oxide decomposes into mercury metal and oxygen. So that's decomposition. It's also oxidation reduction, compound to element. So this one's A and D. Okay, 122, yeah, we can see it. Okay, we got a hydrochloric acid and lead 2 hydroxide makes lead 2 chloride plus water. That's acid base. Let's see. It also forms a precipitate. Lead 2 chloride is a precipitate. So acid base precipitation, no oxidation reduction. Acid base reactions don't do that. So this is B and C. Okay, 123. We're gonna, yeah, well, pushing it. We can't do too many of these things. Element compound synthesis and oxidation reduction. Yep. That's A and C. 124. Oops. Here we go. Water. Yes. I used to have a device that would do that. Use a little electricity. And it would send the hydrogen up the positive electrode and send the oxygen up the negative electrode. You can catch them up at the top and use a glowing splint, and you could stick it in the hydrogen and it would catch on fire. It would pop. Actually, it would pop. And then you stick it in the oxygen and it would catch the splint on fire again. So A and D, oxidation reduction and decomposition. Let's see. Oh, that's it. Those are the only ones that I have marked. So next, what is this? Thursday?
Tuesday.
It's Tuesday? Okay. Thursday, we have an exam on this. Plus, we're going to jump into, no, just the exam. And then the following Tuesday, we'll get into chapter 9. So What I'll do is, I'll fire up the video. You don't have to show up. But if you have questions, then you can ask me in the Zoom. And then you can go take your test if you want to do it online, or you can show up in person, we'll give a paper test. Your choice. That's it for today.